Hello, here is your videos for Lesson 7, also known as Chapter 7. We're going to talk about sampling distributions. Work. So, when we talk sampling distributions, in this class, we're really only going to talk about two specific statistics, which is the proportion and the sample mean. Sample distributions are representations of all possible combinations from a sample size of n. And when you sample from a population, you may not always gain the true mean or proportion, so we use facts about the population to determine how good our sample is and how we can get to our true mean or true proportion. So I need to move this thing. The mean of a sampling distribution of the sample mean of the x bar is the value of the population mean mu. Okay, so the standard deviation of the sampling distribution is x bar is this formula, sigma x bar equals the standard deviation of the population over the sample size, the square root of the sample size. This is the standard error of the mean, or how much the mean varies from the true mean or average, or on average. For a normal population, the sampling distribution of the sample mean is distributed as normal. And when the sampling distribution of x bar is normal, we may standardize to produce the standard normal random variable z, which has the formula there. When we talk about this, we have to talk about the central limit theorem. Given a population mean mu and standard deviation sigma, the sampling distribution of the sample mean x bar becomes approximately normal as the sample size gets larger, regardless of the actual shape of the population. We consider the sample size of n being greater than or equal to 30 large enough to sample to apply the central limit theorem. And I'm going to give you all examples about how this works, so that way there you'll be able to know what the crap it is I'm actually talking about, but this is all the theory behind it. So when we're talking about the central limit theorem and how the samples of the mean are going to be distributed, we know if the population is normal, then the sampling distribution will become normal. If the population is not normal, or the distribution is unknown, and the sample size is greater than 30, then we can say that the sample distribution is approximately normal. And if the population is not normal, or their distribution is unknown and is less than 30, we do not have enough information to determine the shape of the sampling distribution. So that's for the mean. When we're talking sampling distributions for proportions, this deals with the distribution of the statistic p, which we used in the last lesson to talk about number of successes in a binary distribution. So if we take a sample size n from a population proportion, the sample proportion is going to be that x over the n. X represents the number of individuals in that sample that have the particular characteristic that we were looking for. Like from last chapter, an example of that is 19% of CEOs own luxury cars. That would be our P for that problem. So that's our characteristic. So our P hat would be the number of individuals in the sample that have the luxury cars over however many we chose from that sample. We use P hat, that this is read as P hat, to estimate the unknown value of the population proportion P. The sampling distribution of a sample proportion P hat for a given sample size n consists of the collection of the sample proportions of all possible samples of size n for the population. The sampling distribution of any particular statistic for a given sample size n consists of the collection of the values of that sample statistic across all possible sample sizes of n. When we've done our sampling distribution, the mean of the sample distribution of the sample proportion p hat will be p. And we can find the standard error of the proportion by calculating this funky standard deviation equation. So now here's the central limit theorem for proportions. The sampling distribution of the sample proportion p hat follows an approximately normal distribution with mean mu p hat equaling p, and the standard deviation of that funky formula, when the following conditions are met: that your sample size times your proportion is greater than or equal to 5, and, this is an and, we have to do both of these, our sample size times Q, or 1 minus P, is greater than or equal to 5. And the minimum sample size required to produce approximate normality in the sampling distribution of P hat is larger of the either 5 divided by P or 5 divided by 1 minus P. This is the z-score for that particular for the proportions of this is the z. I can't talk. My vocal centers are just shutting down. So here is the z. When we're looking for percentiles or something within distribution of our p hats, we would use this formula to calculate the z-score so we can find that percentile. Again, I will show you in an example so you know exactly what I'm talking about. So we have some examples, so I'm going to stop the video and make a new one